So, what if I told you the answer to one of green energy's biggest problems isn't some brand new sci fi invention? What if it's actually a forgotten piece of industrial tech from World War II? Sounds kind of crazy, right? But it turns out an old, incredibly power hungry process might just be the perfect fix for a major headache in the world of modern renewables. All right, so here's how we're going to break this down. First, we'll get into the weeds on green energy's big problem. Then, we're going to jump in a time machine and look at a WW2 tech revival. After that, we'll see how it's been updated into a modern green process, how it can act as a giant industrial power sink, and finally, what it takes to actually bring this whole thing to life. Okay, first things first, let's talk about that core problem. It's this strange, counterintuitive paradox of having way, way too much of a good thing. We spend so much time worrying about what happens when the sun isn't shining or the wind isn't blowing. But have you ever wondered what happens on those perfect days? When it's super sunny, super windy, and our renewable farms are just cranking out more electricity than we can possibly use? Well, the answer is this really frustrating thing called curtailment. And it's exactly what it sounds like. It means we have to deliberately tell a wind turbine to stop spinning or tell a solar farm to disconnect. We are literally forced to throw away perfectly good, clean energy because at that exact moment, there's just nowhere for it to go. And this isn't just a little waste, it has a huge economic fallout. As Dr. Robert Otto lays out in his letter to investors, when there's too much power, the price can totally crash, dropping by $20, even $40 per megawatt hour. It can even go negative, where the power producers literally have to pay the grid to take their electricity. The whole system actually punishes you for making too much clean energy. But what if you could actually use all that cheap, excess power for something productive? Well, for the solution, we have to look to a really unexpected place, the 1940s. Let me introduce you to the Permanent magnesium plant. This thing was an absolute industrial beast, built during World War II for one reason, to make magnesium, lots and lots of magnesium. It's a super lightweight metal that was absolutely critical for building airplanes and other gear for the war, and the process they used took a ton of energy. So the plant goes up in 1941, and during the war, it's a huge success. But afterward, its biggest feature, that massive appetite for electricity, became its biggest weakness. It just wasn't economical anymore. So the whole technology kind of faded away. But now, that very same trait, its hunger for power, is being reimagined for a brand new, totally green mission. So, how do you take this old school tech and bring it into the 21st century? Because we're not just talking about dusting off old blueprints. This is a complete high-tech overhaul. The basic chemistry might be the same, but the engineering, it's a whole new ballgame. The real secret sauce, the core innovation, it's all about cooling things down. The original way was pretty clunky. They used huge amounts of natural gas to slowly cool down the magnesium vapor. The new way is so much more elegant. It just injects a tiny spray of a special liquid coolant to do the job almost instantly. And I'm not being dramatic when I say instantly. Listen to how the provisional patent application itself describes it. The coolant explodes into a vapor state. I mean, come on. It's basically a controlled micro-explosion that flash freezes the magnesium gas into tiny solid powder in a split second. It's unbelievably fast and efficient. So the whole process is just beautifully simple. You make the magnesium gas at super high temperatures, you hit it with that liquid coolant to get that rapid condensation, and then you use simple ceramic filters to collect the pure magnesium dust. But here's the most brilliant part. The coolant that turned into a vapor, it gets captured, turned back into a liquid, and pumped right back to the beginning. It is a completely closed loop. Okay, so we've got this super efficient process that loves electricity. How does that actually help with our wasted wind and solar power problem? This is where this really cool idea of a power sink comes into play. A power sink is pretty much what it sounds like, a factory that's designed to be a giant energy sponge. Think about it. Most factories need a steady, constant stream of power. This one is designed to be flexible. It can soak up enormous amounts of electricity when it's cheap and plentiful, and then dial it back when power is expensive and in high demand. And we are talking about a massive scale here. This plant is designed to gulp down up to 155 megawatts of power. That is a huge load that can be switched on specifically when the grid is overflowing with renewables, effectively turning that wasted energy into a really valuable physical product. This chart just shows you how brilliant that flexibility is. It's not just an on or off switch. It can just sip a little power to keep things warm. It can run at a normal production level, or when the grid signals that there's a ton of cheap, clean power available, it can ramp all the way up to that peak power sink mode. It literally adjusts its appetite for the grid's needs. So what you end up with is this perfect win-win-win situation. For the grid, you're getting stability, you're cutting down on waste and helping to stop those crazy price swings. For the business, it's a huge economic advantage. You're using the cheapest possible electricity to make a high-value metal. And then there's the sustainability win. The process also captures carbon monoxide, which can then be used to create next-gen e-fuels. This all sounds amazing on paper, right? It's a fantastic idea. But how do you actually get something this big off the drawing board and into the real world? Well, you should know this is way more than just a cool theory. A super detailed provisional patent was filed in late 2025. This thing lays out all the engineering, the chemistry, and the entire business plan for how to commercialize this, starting with a smaller pilot plant. And the really good news is the money is there. There's already a whole ecosystem of investors who are hungry for exactly this kind of project. You've got your early-stage VCs looking for carbon-cutting tech, growth equity firms who fund big industrial projects, and these massive infrastructure funds looking for large-scale assets. The capital is out there and waiting. But look, a project this huge, it needs more than just a big check. It needs some serious strategic brainpower, and that's where groups like the BCG Henderson Institute are crucial. They can provide things like scenario planning for market ups and downs, the complex energy modeling that gives investors confidence, and they can build the public case studies that attract even more partners. Which brings us right back to that big question at the beginning. It's kind of an amazing thought, isn't it? That a power-hungry relic from our industrial past, supercharged with modern innovation, could become the missing piece of our renewable energy puzzle. A giant, flexible battery that turns our biggest challenge into one of our biggest opportunities. The past, it turns out, might literally be the key to powering our future.